Have you ever wondered why we need different sets of numbers? Imagine you are sitting at a soccer match. You absolutely need to count the players. And if the players are skilled, then the goals scored by the team. These numbers can be positive integers or zero. At the start of the game, a team will have 0 goals, and then this number can start increasing 1, 2, 3, and so on. A team will never have -1 goal. In the worst case, they will only have 0. These numbers are called natural numbers. The natural numbers, therefore, are the set of 0 and positive integers. This set is typically denoted by a stylized letter N. Let's think a bit further and imagine that we can only express numbers using natural numbers. We want to describe the air temperature in degrees Celsius. On a summer day, this wouldn't be a problem, as we could simply say it's 20 degrees. However, on a winter day, the temperature could be negative, for example, -2 degrees. We cannot express numbers smaller than 0 using natural numbers. So, we need to expand our set of numbers to include the set of integers. This set now includes negative integers as well as natural numbers. The set is denoted by the letter Z. Imagine that you are sharing a single pizza with your friends. You cut the pizza into slices and want to express what fraction of the whole pizza each person gets. This cannot be done using integers because we only have one whole pizza. We need to introduce fractional numbers. In this way, we expand our collection of numbers with yet another set. This set of numbers is called the set of rational numbers. Rational numbers are those that can be expressed as the quotient of 2 integers. Rational numbers cannot describe certain shapes or geometries. For example, we know that the diagonal of a square with side length 1 has a length that is the square root of 2 times the side length. This can be calculated using the Pythagorean theorem. The square root of 2 is not a rational number. We use another number to determine the circumference and area of a circle. This number is pi. You've probably heard of the golden ratio. It is a proportion that is very pleasing to the eye. Logo designers, painters, and architects often use this ratio. But it also appears in many places in nature, such as in the spiral structure of a seashell. This ratio is also a number that cannot be expressed using rational numbers. In addition to rational numbers, we need to introduce irrational numbers. Irrational numbers are infinite non-repeating fractions, meaning their fractional part repeats randomly and infinitely. Rational fractions can also be infinite in length, but they repeat in a certain pattern. For example, 1/3. The decimal point is followed by an infinite number of 3s. Why is it beneficial for us to have both rational and irrational numbers? With the help of these two sets, we can describe continuous changes. For example, when you travel from the city to the countryside. Let's assume the car is leaving a paint stripe behind as it moves. The stripe would be a continuous line from the city all the way to the countryside house. If, for example, we didn't have irrational numbers, this line would be dotted in certain places. This would mean the car would never pass over those specific points. But that's impossible because the car can't teleport over the gaps. The car was moving continuously, and at every moment we knew exactly where it was. To describe this, we need real numbers. Real numbers cover all the numbers that can be represented on the number line. Let's look at one more special set of numbers. This is the largest set, the so-called set of complex numbers. Complex numbers were created by extending real numbers and allow us to solve problems that cannot be addressed with real numbers, such as the square root of negative numbers. Why are complex numbers important in practice? For example, if we have a swing and want to describe its dynamics, we will be able to handle and interpret it easily using complex numbers. In engineering practice, they often appear in oscillating, vibrating motions. These include electrical engineering problems, telecommunications, and control tasks. or even graphical transformations in computers. With this, we have come to the end of our summary of number sets. What does it mean for a set to be countably infinite? According to the definition, if we can assign another number to each natural number, then the set of these other numbers will also be countably infinite. Let's look at an example. Take the natural numbers. Start with 1, then 2, 3, and so on up to n. We say that these numbers are countably infinite. Now let's try to assign exactly one other number to each of these numbers. Let's say we assign the negative value to each natural number. In other words, we take the negative of each one. It's clear that each natural number has a pair. Therefore, if the natural numbers are countably infinite, then the negative integers are also countably infinite. Let's quickly look at another example. Take the double of each natural number. We can see that they can again be paired with the natural numbers, so they are also countably infinite. Let's see what happens in the case of fractions. Let's pair each natural number with a rational number. Rational numbers can be written as the quotient of two integers. Let's create a table where the row and column numbers are natural numbers. Let's create fractions where the row numbers determine the denominator and the column numbers determine the numerator. We can assign a denominator to each row. And we can assign a numerator to each column. Therefore, for every natural number, we can also find a rational number. If we continue this way all the way to n, we will get the positive rational numbers. This can also be done for the negative case. We can say that rational numbers are countably infinite because we can pair them with the natural numbers. Let's play a game. Let's see what happens if I say that we assign the value of 1 to each rational number. In other words, wherever there is a rational number, the value of y will be 1. On the number line, we get a straight line. In the next step, we assign the value of 0 to each irrational number. We can only plot points, because between irrational numbers, there will be rational numbers. And between rational numbers, there will be irrational numbers. In both cases, we do not have a continuous line, but a set of points. There are even more numbers between the numbers. And even more. And even more. In the end, we will have so many points that we won't be able to distinguish them from each other. But we know that they are made up of many points. In this case, we won't get a continuous line. There will always be an irrational number between any two rational numbers. Once we connect the rational and irrational numbers, our number scale will become a continuous line. In other words, we can describe every number that lies on the number line. These will be the real numbers. Real numbers are uncountably infinite. We have reached the end of the episode's material. Thank you for watching the video. If you found it helpful, don't forget to subscribe. Be sure to check out the other videos in the course to continue building your knowledge. See you next time.